Okay, so welcome back to part 2 of our ionic bonding, which will hopefully be a bit shorter than part 1. Okay, so now we're going to be looking at the properties of ionic compounds and a bit more on how they're formed. So one of the reasons that we're looking at this is, as we've mentioned, the idea that by the way things bond, it controls the type of properties that we see. And one of the most interesting ways for us to see this and to look at this in practice is if we look at the form of sodium chloride and how it's made. So sodium, as we've looked at in terms of metallic bonding, is a group 1 metal. So we can see it here being under oil to keep it from reacting from moisture in the air and the oxygen. So as a group 1 metal, it's very reactive and it wants to lose its electron to form sodium plus and get that full electron shell. And then we have here in B here, this is actually chlorine gas, which is a green gas. When we react these two together and use a catalyst to kick it off, we get a very exothermic reaction that gives off a lot of heat and light, which is quite a spectacular reaction to see. And at the end of it, we end up with sodium chloride, the ionic salt that we use on our food for actually making things taste better or enhancing flavor or preserving food. The interesting thing about this, of course, is if we think about sodium, it's a dangerous metal, certainly would cause a lot of damage to us if we ate it. And something like chlorine, well, chlorine's a toxic gas. So while chlorine is covalently bonded, it's dangerous for us if we breathe it in. Sodium with its metallic bonding is highly reactive and would cause us burns and is toxic. But when we react these two together, we end up with something that is completely safe for us to eat. And this is all as a result of the formation of those ions, stability and bonding. Okay, so let's look at this. We've already talked about this. Ionic bonds are formed between metals and non-metals. So we need to be able to look at them and go, is it two metals or a metal and a non-metal or two non-metals, and determine what type of bonding. If it's ionic, it will always be a metal element bonded with a non-metal. Okay, and then this is formed when the transfer of electrons from the metal to the non-metal, and then the electrostatic attraction between the newly formed ions. Okay, so when we look at that in drawing diagrams for it, what we end up with is when we have Na plus and Cl minus, we end up with this negative charge, positive charge, which is attracted to each other, forming a ionic bond or an ionic bond. Okay, when we draw a diagram for that, remember, and we use our Bohr shell notation to show the transfer of the electron across to the chlorine. They have the electron configuration 281 for sodium before the transfer, 287 for chlorine before the transfer, the arrow to show the transformation, and then we've actually drawn them closer together now due to that electrostatic attraction, and with the new electron configurations for the Na plus ion being 2,8 and the chloride ion being 2,8,8, and our new compound, sodium chloride. Okay, so anytime you're asked to draw a diagram illustrating how the bond is formed, this is what it's asking for. Okay, just another example, magnesium chloride. Okay, sometimes we need more than one anion to balance out the charge. So magnesium has 2 to donate, so it gives 1 to one chlorine, 1 to the other chlorine, forming MgCl2. Okay, so remember, you need to be able to draw these diagrams as well. Okay, so that's how our lattice forms. They don't form as just individual atoms like 1 magnesium and 2 chloride. When that happens, it forms an overall lattice. We get millions and trillions of magnesium and chloride atoms lining up, forming a strong lattice. Okay, so every ionic compound is made up of alternating positive and negative ions. Okay, they'll be arranged in a 3-dimensional crystal lattice similar to the one we looked at with metallic bonding. Okay, the lattice is held together by strong electrostatic forces, remembering that the strength of the force is linked to our melting point. So ionic compounds have high melting points as well because of the strength of that force. Okay, ions in the lattice are packed tightly, okay, and they're always arranged so that things of the same charge are kept as far apart as possible. Okay, so if we look at the way that they're arrayed here, we have chloride anions with sodium surrounding around the chloride in this three-dimensional pattern. Remembering that we can tell the two apart because the chloride anion is going to be much bigger in size than the sodium cation. Okay, remembering anions get bigger, cations get smaller. Okay, so again, another three-dimensional structure here where we've got the sodium ions this time in purple and the chloride ions in green. So in this case, the electron transfer has already occurred. And in order to make sure that they're kept as far apart as possible, every sodium atom is going to be surrounded by 6 chloride ions. Every chloride is going to be surrounded by 6 sodium ions. And this can only happen if it arranges in a particular way. Okay, so each individual ion will be strongly attracted to its neighbor, which means we get a very strong structure. And this is our ionic bonding model. Okay, so now we've got the model. Remember, we need to link our properties to the model. So number one, they usually form crystalline solids, and we've talked about this a lot already. Okay, so that regular pattern ordered array that gives regularity to its structure. So we see crystals and geometric shapes like we've looked at in class. High melting points and boiling points. They don't conduct electricity in the solid form. Okay, they're hard, so they're often very difficult to scratch. Okay, if you think about gemstones, that should be easy to remember. They're usually water soluble, okay, and will dissolve into separated ions in solution. They will conduct electricity when they're in the liquid state, okay, so this is when their state symbol is L. And that is when we've melted it down. It's molten, okay, like melting ice. What that does is freeze up all the ions so that they can roll over each other, but it's molten, okay? Not to be confused with aqueous, which is where they will also be able to conduct electricity, but they will have the symbol AQ, which means that they're in solution with water. Okay, so the ions are freely moving around in water. These are very different if we have a molten salt. Okay, and then the last one, they're brittle, which means they shatter when a force is applied. So when we explain these, we take the same approach we did with metallic bonding. Okay, so let's look at our crystalline solids and melting points first. We can explain the crystalline solids by linking it back to the solid structure of ionic compounds, coming about due to the repeating, highly ordered three-dimensional arrangement of the lattice. So when we see these regular formations, it's because of that repeating nature. Okay, high melting points and boiling points, again, this is because of our strong attractive force between oppositely charged ions. Remember, we always have to say what it is and then what it's between. So in this case, oppositely charged ions. And the stronger the bond, the more energy is required to separate the ions. So if it's a +1 and a +1, that would be a weaker bond than, say, a +2 and a -2, okay? Remembering that magnitude of the force counts as well. So hard, we've talked about hard when we talked about metals, and for much the same reason, because the ions are held tightly in the lattice, they are hard to remove, okay? So it makes it hard and resistant to physical change, okay? The one that we really need to be able to talk about and not get confused on is our not conducting electricity in the solid state, okay? And this guy here is to remind you that in order for a substance to carry an electrical current, so be conductive, the charged particles need to be free to move. So in this case, we would have to, because the ions are held in place, okay, they're not free to move, they're not moving through the substance like the electrons do in a metal, then it won't conduct an electric charge, okay, because they're tightly organized and they're held in place. So it won't conduct an electric charge, okay. So Strong attraction between positive and negative, held strongly, so high melting points and high boiling points, but don't conduct electricity. Okay, water soluble. We'll talk about this more when we do water, but essentially, because water is particularly special and has partially positive and partially negative character, it can get in between the positives and negatives in our ionic lattice, surrounding our charged species and stabilizing them and carrying them off into our solution. So it disrupts the lattice and frees up the ions. So that means, hopefully you can put 2 and 2 together, when we have aqueous solutions, we will actually see it conducting an electric charge. Okay, pure water won't conduct electricity, solid salt won't conduct electricity, but if we combine the two, then our light globe will glow because we have an electric charge that is able to be carried through the solution. Okay, anytime we have an ionic substance dissolved into water, we refer to it as an electrolyte. Okay, and you may have heard of electrolytes previously, and we talked about them last time, in that things like Gatorade, Hydrolyte contain charged particles, and we refer to those as electrolytes as well. Okay, the other one to remember when an ionic compound is melted, which can take up to 1800, 1900 degrees C, the ions are free to move, okay, so they will conduct electricity, okay. Then one of our last ones, looking at ionic compounds being brittle. I know that a number of you have already spoken to me about this one. You have a pretty good handle on it. So essentially when we apply a force to the lattice, like we did with metals, instead of the lattice shifting and being stabilized because of the delocalized electrons, now what happens, we apply a force, we get a shift in the lattice, which causes positive and negative charges to align. When they do that, they repel each other and it causes a shatter. Okay, it breaks the crystal apart and it will shatter apart rather than bending like the metal does. Okay, so applied force, the lattice will shift and we will get this repulsion between like charges, making the structure brittle, but remember, very hard. So that's it for properties, okay? We'll talk about these more in class, but as with metals, these are the properties you have to know and you need to be able to sum these up and explain them during the models. So I'll see you next in class.